Cool. All right. So properties of colloids, that's what we're going to be doing, as you can't see by this sheet of paper. So the first thing you need to know whenever you're doing colloidal properties is the Van Hoff factor. In a solution, some solutes will dissociate into ions. All of the ionic compounds will basically do that. So good thing to know. Might be wrote like MX or M2X, MX2, just depending on what you see. But I mean, basically, I mean, like M2X would be the same as, well, that's a stupid example. Let's see, like KO2, that probably, no, potassium's still a group 1 cation. Like CaO2, there you go. That's one that probably exists in nature. So if you see that, it's synonymous. Strong bases and acids, they'll dissolve. I mean, if you see like HCl, that's going to dissolve into a hydrogen and then a chloride, negative, positive. So you'll have both of those going through. And if it doesn't dissociate, the Van Hoff is going to be 1 for it. That's for like a glucose, a couple of, I mean, a lot of the just covalent compounds really aren't going to do too much. Hydrocarbons are a big one. And then if you see I in a formula, that means it's the Van Hoff factor. And you need that for basically all of the colloid properties. So be familiar with it. And that's just a picture at the bottom showing how they dissociate into ions. So first colloid property we're going to be talking about is vapor pressure lowering. And basically that just means more solute, the more pressure is going to be exerted on the solution due to the particles wanting to vaporize less. So the more solute you have, the less vaporization, I guess, on top of it. I mean, basically. And the way that I like to think about colloidal properties in general, basically, is it just extends the liquid state. So I mean, you can see it rather would be a liquid. It'd rather be a liquid with more solute, right? Than up there. There's more liquid. There's more vaporization up there. So where we have more liquid, that's the colloidal properties coming into play. They just extend the liquid state. We got the freezing point depression over here, which we'll talk about later. It extends the liquid state that way, and then the boiling point elevation extends the boiling point that way. So there you go. And now we can finally get into a little bit of practice with it. And this is going to be the vapor pressure lowering. Now, I did work through a little bit of it already, so spoilers, because I was a little bit stupid and messed up the molar masses, and this is my second attempt recording this because I'm dumb. So anyway, let's still get into it. The vapor pressure of pure benzene is 100 torr at 26.1 degrees Celsius. Calculate the vapor pressure of a solution containing 24.6 grams of Campor dissolved in 100 milliliters of benzene. The density of benzene is 0.877 grams per milliliter. So what's the first step here? So the first step, we have grams of everything right now, right? So we have the 24.6 grams, and then we have the grams per milliliter. And since we are doing the vapor pressure lowering, we're not using gram units for molality or anything. We are going to be using moles for mole fraction. So what do we need for mole fraction? Well, we need the 0.877 grams per milliliter to turn into moles. So how do we get that to turn into moles? That's just going to be a simple 0.877 grams times the benzene, which I already looked up, did it last time. It's around like 78.01 grams. Let me make sure we got our little cheat sheet right there. Yes, it is. There you go. Let's erase a little zero there. All right, so it's times 71.1. Now we have moles, and now we need to divide out those milliliters because we still have those milliliters there, and now those milliliters will cancel out. So we wanted moles. We're going to end up with the only unit left being moles. So since that cancels out there, let's do a little quick math calculation. See what that comes out to. Alright, so what you should end up with, at least if you're like me, and I'm not the smartest tool in the shed, so hopefully you're not like me, it's 1.123 moles. So that's what we've got for the first one. And now, for the rest of it, I realize I covered the problem completely. But for the other one, we need to do 24.6 grams and then multiply that by 1 mole. You don't have to do the milliliters here because it just gives you the grams. You don't have to divide it or multiply out the milliliters to get it to cancel out. And this molar mass, hold on, I'm just going to cheat. 152 grams. So let's do another quick calculation. 24.6 divided by 152 should get 0.1618 moles. So now we need the mole fraction of the solvent, right? So, and you can see by the equation, since we have this, that is going to be for the, I haven't even done the equation yet, sorry. So basically the equation for this is going to be P solution equals the mole fraction of the solvent times P starred or P naught of the solvent. So we have P naught of the solvent, and that's going to be 100 torr. Now we need the mole fraction of the solvent. How do you find the mole fraction? So for the mole fraction, our solvent is going to be the benzene. So in order to do that, we will just add up the 1.68 or 0.1618, excuse me, plus that. See what you come out with there. Should be about 1.2848, and then we're just going to take 1.23 or 123 out of that, and see what we come up with. We're going to get 0.874 as our mole fraction. So now we have our mole fraction. We have everything we need to get the P of the solution. So mole times the P of the solvent, 100 torr, and that's going to equal the solution. So let's see what we get there. Spoiler alert, you just move the decimal twice, but you should end up with 87.4. It'll be in torr. So that should be your answer for that one. All right, next one. Oh goodness, the next paper's really messed up now. But let's get into the freezing point depression and boiling point elevation. So more solute, that's going to lower the freezing point. An example, the salt on the roads. Why do they put the salt down? It takes more coldness to make the ice stay on the roads. So that's why the salt goes. And inversely, more solute will also raise the boiling point. So like we talked about earlier, just extending the liquid phase, that's basically what it does. So that's your colloidal properties. And this is known as boiling point elevation for that. So on to an example problem. So we have ethylene glycol is a common automobile antifreeze. Calculate the freezing point in a solution containing 651 grams in a 2,505 grams of water. The molar mass is 62.01 grams per mole, and then the freezing constant is 1.86, boiling constant is 0.52. So we have everything that we need in order to find the freezing point depression. So first things first, let's write out the formula. Didn't do that first last time, but I'm sorry. So times molality times I. Oh, also, I'm going to go back to the last one real quick. I'm sorry. If benzene did have a dissociating factor with it, which it doesn't, but if it does, you would have to take into account the Van Hoff factor. So it'd be that. Sorry, but it doesn't have that. So you don't have to worry about it that time. Just thought I'd mention it. So anyway, we have the Kf times m times I, and that's going to equal the delta Tf. And that's just the delta. So that's not going to be your boiling point. That's just going to, or freezing point, excuse me. That's just going to be how much it changes. So the easy thing, let's calculate the molality first. So I'm just gonna get this out of the way. So we have the denominator, right? And now we just need the numerator. So ethylene glycol, and I'm sorry, but this is another molar mass we're just gonna have to look up here, and that is going to be 62.1. So 62.1 is going to be that 62.1 grams over moles, and that's going to equal 10.48 moles. And this is solute, that's solvent, right? So now we divide that out. .184 is going to be the molality. And then we need the constant, which is right there. And is it a dissociating ion? Let's see. Well, it's not a strong acid. It's not ionic. So, no, it is just going to stay as it is. Some people may see the hydroxide in them and be like, whoa, it's basic. But that's not true. It's just a hydrocarbon with an OH bond. So, unfortunately, there is no Van Hoff factor to put in there. So we have our Kf, we have that, and now we can find our change in freezing point. Which will equal 7.78. You multiply both of those, and we know that the freezing point of water is 32, or just Fahrenheit, is 0. So I mean, basically, you just it's that because it's water. So freezing point of water normally equals 0, and since the change is that, you just put a negative sign. But I mean, it's the normal freezing point minus change in TF if you really want to get deep into it. Alright, so boiling point. Same thing. Basically. It's just oh, sorry. Should have put that there. And that would make that equation positive. Whichever one you want to do. Just know it makes it go down. But boiling point, so now we do KB, so we do a different constant, and now it's still molal, and then we still got the Van Hoff, which isn't applicable in this equation, but still needs to be remembered. So, molals. Let's get the molality of it first. Well, good news for us, we already have that. So, we just put in the same number because it was shown up here. We already did the work where it's going to be the moles over the kilograms. So we have moles and kilograms. And now we just have a different constant. That's the only bit of difference here. So let's multiply these up. And that will equal 2.1756, and we'll just knock it down for sig fig's sake. Alright, so, and what is the units for this? Degrees Celsius, degrees Celsius. And that's going to be your freezing point depression. So lastly, we'd have the osmotic pressure. And, I mean, this one's a pretty important one for a variety of reasons, but it works mainly with like selectively permeable membranes. So the solution, once in solution, it makes it harder for it to come over that selectively permeable membrane, and this is really good for finding molar mass. So small changes in solute can make big changes in osmotic pressure. That's how molar mass is found very accurately. Technically, you can do it from the freezing point depression or the elevation, but it's just not as accurate of a measurement. So osmotic pressure. So calculate the concentration of urea that has an osmotic pressure of 30 atm at 25 degrees Celsius. So what is the formula for osmotic pressure? So osmotic pressure looks like a pi symbol, and then you're going to have big M, because it's molarity, not molality, and then R, and then T, and then I. Alright, so MRTI. So how will we be doing that? It just, okay, yeah, so yeah, 30 ATM. Sorry, my bad. I looked at that and I was like, how'd you get the ATM? Yeah, because the osmotic pressure, that's in ATM units. So that's what we have. We're looking for the molarity. R is going to be the smaller R value of that, not that one, which you can find in like unit cells and stuff. And then the temperature is going to be 298 because it's that plus 273. All right. And then urea, technically it's a weak acid, but really, I mean, it's the Van Hoff factor is negligible. So now we have this. It's just going to be algebra from there. I mean, literally just divide out these. And then you're all good. So let's divide those out. So that should be what you get for your molarity, is 1.226. And that's your osmotic pressure calculation. So real quick, just a sort of review. I love tables, so quick table coming in. So whenever the solute goes up, freeze point goes down. Whenever solute goes up, boiling point goes up. Solute up, vapor pressure up. Solute up, osmotic pressure down. TF is for the temperature of the freezing point. TB, temperature of the boiling point. Vapor pressure is VP, and then like of the solvent, it's going to be like P, and then like a star or not sign, and then osmotic pressure is pi, or something that looks like it. Formulas, so you have delta TF equals negative KF times M times I for freeze point. For boiling point, you have delta TB equals KB times molality times I. So both of those are molality. Sorry, didn't say it last time. And then for vapor pressure, it's the pressure of solution equals mole fraction of solvent times pressure of solvent. And then osmotic pressure is going to be osmotic pressure equals molarity times the smaller R value that you'll see times temperature in Kelvin times the Van Hoff. So, and this can also be multiplied by the Van Hoff. So that's colloidal properties. Yeah.